All right, kiddos, in this video we are going to talk about chair conformations for cyclohexanes that we ended our last video with. And remember, your chair conformation is that you've taken your 6-carbon ring, and instead of all 6 carbons being in the plane, which is definitely not going to work because of angle strain considerations, we're going to push one up and one down. And what that should leave you is with a situation like this. And how you know that, like, if you've got the model right, is that you push it up and you've got 3 carbons sticking straight up and 3 hydrogens sticking straight up, 3 hydrogens sticking straight down, and then 6 along the equator, along the middle of the molecule. And that would let you know that you have that model made correctly. So now let's talk about how to draw the chair conformations, because drawing them is one of those things that I'm going to show you how you should sort of standard do it if you're not using a stencil. And by the way, stencils are great. If you can use one, use one. But it's one of those things that you want to practice a few times, okay? Don't just watch it done once and assume that you're going to get it right, because it's one of those deals that if you don't draw it somewhat correctly, then when you start to add everything else into it, it starts to get really ugly and you can't tell where anything is, and it just leads to some conceptual confusion for you later. So make sure that you're drawing it correctly. So to draw it correctly, what you want to do first is draw a really wide V, okay? And I'm going to draw a really big one first. When you're drawing smaller ones, you can do that. But I think it's really helpful to sort of draw them pretty big first so that you can get the general pattern down, and then you can come back to draw the smaller ones. So really wide V. Then I'm going to draw an angle down here that is about a 60-degree angle. Okay? Essentially, if you drew actually like a perpendicular line like straight down here, then that angle is going to be a 30-degree and that one's going to be a 60-degree. So 30 degrees from a perpendicular sort of dashed line there. Okay, and then we're going to draw our next line. I'm going to draw the next line. So I've got my 3 baselines. Everything else is going to be parallel to one of these lines now. So my next line is going to be parallel to this one. And I'm going to draw it up so that it's not quite as far. Again, if I drew like a little dotted line here, I'm going to draw this one not quite as far, okay, as that one. And I've already made a little bit of a mistake. I'm not quite parallel. I probably came up a little bit too much, but you'll see why here in a second. Okay, so now that I have that one drawn, I'm going to draw a line parallel to this one, running basically the same course. It's starting up here just like that one did. Angle should be about the same, and it's going to end in about the same spot. Okay, and then we're going to come back in and I'm going to draw that last connecting line there. Maybe clean up if it doesn't look super pretty there. And now if you draw this and these 2 lines are like running into each other like mine are, then you'll probably have your angles off a little bit and you want to retry that. But that's the basic shape of your chair model. It looks sort of like a bow tie. It looks like a very skewed bow tie, right? Not just tilted, but like things are skewed and maybe a little even stretched out a little bit. Okay, so that's the basic structure. I'm going to erase that one, then we're going to draw one again, just so you can make sure that you're getting the basics of drawing it down correctly. All right, so hopefully you've drawn a bunch of chair models at this point, made sure that you've got everything sort of straight there. So now the next thing is I need to somehow represent where all of my hydrogens are. And this is going to become more important when they're not hydrogens really, but you need to make sure that you're getting all your hydrogens in the right place. And so we're going to draw 2 types of hydrogens on our model here. The first of them are the hydrogens that are going straight up and straight down. Those hydrogens have a name, and I'm going to label all of those in blue on this diagram. They're called axial hydrogens. They're on the axis. If we were treating the plane of this molecule, okay, as like the Earth, then they're going straight up through it. That would be the axis, okay? Yes, I know the axis is tilted. Ignore all that, okay? So we're going to start with this one. It's just sort of by convention that we draw the first hydrogen straight up on the upper right-hand corner of this particular chair model. Okay, and so that's straight up, and then the way that it works is that if one is straight up, if you'll notice on your model, if one is straight up, the next one is straight down, straight up, straight down, straight up, straight down, and so you're going to alternate them as you then go through. And the axials are the easiest thing to draw, so we're going to draw those first. Okay, so up, down, up, 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 down. This, by the way, is where you would sort of get a clue that, perhaps I botched up drawing my model, because if you don't draw it, or if you draw it sort of lopsided or compressed or whatever, then these two axials will run into each other, and that's not the way that's going to work at all. So if you spread them out properly, you shouldn't really have any problems with that. So those are the axials. The other ones that we're going to worry about are our friends, the equatorials. Okay, so let me write that out. Okay, so our equatorials are the ones, so we did the up and downs. The equatorials are the ones that are sticking out from the equatorial plane. Like if we were treating the carbon ring sort of as a globe and we said the straight up and down was the axis, then around the middle here would be the equatorials. And if you look at them, what's going on with them is that if I've got a down axial hydrogen, then I have a slightly up equatorial. And so they're not straight equatorial. They're not like sticking straight out along the plane. First off, there's no one plane anyway, right? Because the carbons are all slightly out of plane with each other. But they're not sticking straight out. Rather, they're sticking a little bit down, a little bit up in their equatorial. And so after you draw your axials, so for instance, I know that if I drew this axial up, that the equatorial is going to be going down. And so the question then is, like, how do I draw it going down? Well, it's actually pretty straightforward and simple, which is that I'm going to draw that equatorial down parallel to this particular line here. And so I've got my down there. I come back over here, and we've got it up equatorial there. The question here for the equatorials, what really sort of starts to throw students off then is when they're drawing the equatorials here, like which way does it go? Remember that you're making it essentially parallel to a bond 2 over, okay, or 1 over, I guess. So we're here, carbon, and then that one, it should be parallel to that. And so that means that I've got a down going that way, parallel to that line. Okay, we come back over here. Remember, I should now be parallel here, and this one should be going up, right, because the axial is going down. Okay, let me make sure that I'm out of the way of the frame there when you get that one drawn. Okay, so that one's equatorial up, and really, to be honest, I probably should have, really, to be honest, it would be better if I probably should have drawn that a little bit more plainly parallel, a little bit flatter. Remember, they're equatorial, so they shouldn't be going straight up and down. They should be just slightly angled up. Okay, so that one was up. That means that the next one then is down. Where is it down to? Like, what direction do I draw that guy in? So I'm going to draw that down that way. Again, it should be parallel to that. I probably should have angled it down just a little bit further there. And then for the next one, we are going that way. And so that is going to represent our three-dimensional model here, where you've got 3 upward axials, 1, 2, 3, alternating with 3 downward axials, okay? And then we've got 6 equatorials, those are the yellows, and 3 of them should be going up and 3 of them should be going down as well. And so that's how you're going to draw each of those particular models, okay? And I'm going to erase this and I'm going to make it a little bit smaller, and we're going to talk real briefly about something called a chair flip. All right, so everything we're doing here is about conformations and about what's more stable. So we now have a situation where I've substituted one of my hydrogens for a chlorine. And so if you sort of visualize the ring here, okay, this is the situation that we've got. Chlorine, I've got it in an axial position. I've got it up here in the upper right. So chlorine up here in the upper right. And cyclohexanes undergo a conformational shift that we commonly refer to as a ring flip. And ring flip makes it sound like I took it and like flipped it over like this, which you're like, how is that a conformational shift? It's just turning the molecule over. And you're correct. That's not a conformational shift. That is just flipping the molecule over. So a conformational shift, if you remember all the ones that we've done so far in the previous videos, have been us rotating things around a single bond. And now I've got obviously 6 single bonds here. When I rotate this though, I'm going to rotate it in such a way that I'm rotating all of the single bonds, okay, such that I'm still going to end up with a chair conformation, but the chair conformation is essentially going to be a mirror of this one. And what you're going to see is that causes some shifting of where things go as far as doing our drawings of it, okay? And so I'm going to take this now, I'm going to bend this down so that it becomes my down, okay? And when I do that, I'm going to shift everything else around just a little bit, okay, such that what was my, let me make sure that I've got everything shifted the way that we wanted to get it shifted so that we're still in our chair conformation. Okay, so chair conformation, I've essentially shifted around every single bond, but I've shifted it in such a way now that if you'll notice, my high end now is on the left-hand side for me, probably your right-hand side, but my left-hand side, whereas it was on the right-hand side over there. In other words, I've got something sticking up there. My chlorine now is shifted a little bit, and what was now up is now shifted down a little bit, and the overall shape of this is going to change. So let me draw this, and then we'll talk about what actually shifts there. So I haven't added anything else onto my model yet. What I did, though, was I drew the flip. So this is sort of your standard chair conformation, the way that you would normally start drawing things. And then I flipped it, and I flipped it again by taking what was the carbon that was sticking up out of the plane and pushing it down to be the bottom one, pushing the one that was at the bottom and pushing it up to be the top one. Okay? Now what that means, and this is really super important for us, what that means, and this is really important for us, is that this chlorine that I had sticking up here is no longer at like this carbon, because that carbon is no longer up there. That carbon is the one that I pushed down out of the plane. It's now down this way. And if you look at our model of it, okay, and this is exactly what I did, okay, I pushed the top carbon down and the bottom carbon up. This chlorine is still up. It's still on this side of the ring, which is going to be real important for us when we talk about cis and trans isomerism here in the next video. So this is really important that it's still up, but it's not on that up carbon anymore. It's now going equatorial. It's not axial anymore. It's equatorial. And so I'm going to go ahead and draw that one so you can see where that went. That is now my substituent that is right here. It is equatorial up. Now what's important here is that if I drew everything else, I would draw everything else the normal way. And by the way, these are hydrogens. These are not methyl groups. I know that's a little disconcerting, but when you first start drawing these, you're going to draw them as hydrogens just so you know where everything goes. So I still have an axial up here. I'm still going to start that same way. Axial down, axial up, axial down, axial up, axial down. Okay? But essentially what this does is it almost makes it as though we had like a rotation. Okay? So this carbon essentially rotated down to become this carbon down here. Everything still stays on the same side of the ring that it was on, but its position is shifted, and it's almost like it's done one clockwise rotation as far as where the carbons are. And please make sure you get this. This chlorine didn't jump to this carbon. This carbon shifted conformations. It shifted its position in the molecule to be the one that was going up. Okay, the carbon that was going up to now the carbon that's going down. The chlorine is still up, but it's not sticking straight up as in axial. It's sticking equatorial up out at an angle. Okay, now this is why conformations are so important for cyclohexanes and for chair models. We're going to work a lot of these in class, but what's really important here is that this conformation, and hold on, let me go back and draw the hydrogens in here real quick. So let's see here. We've got hydrogen. Okay, sorry, I had to go back in and draw our equatorial hydrogens. So what's really important here is that there becomes a big difference here in the way that everything is set up. So I'm going to shift this back, okay? So this is this model now. I'm going to chair flip it back to become this model again. Again, my chlorine now becomes one of my axials. Everything else shifts its location, okay, a little bit. So let's see, up, down. You'll know that you've got it right when you've got 3 up and 3 down, right? I mean, that's how your chair conformation should work. So that's this original thing again. Now, what's going on here is I've got this big old chlorine up here, or let's say that it was a methyl or an ethyl group or whatever. I'm getting some strain up here when it's on top against these other things. And so we got some torsional strain there. If we look at it along certain lines, those things are overlapping. We've got less here than we had before. And so we've got some strain up here because this is up here. Essentially, if we drew this in a Newman projection, we would see that we're essentially having a gauche interaction. It's called a 1,3 diaxial interaction. And we're not at the level that we're going to worry too much about that. But what matters for us is that if you have the larger group in the axial position, whether it's up or whether it's down, it has a lot more interference. There's a lot more strain up here than there would be that if we shifted it back down and made it equatorial. Okay, and why is that? Well, let me do the shift here real quick, and then you'll sort of be able to see why that matters so much. Okay, so again, 3 up, 3 down, but now my 3 up are all my hydrogens instead of my chlorine. Now, what is this big chlorine group interfering with now? And the answer is nothing. Okay, it's sticking out of the end of the molecule. It's not really, there's no strain there from that molecule at all. And so what that means for us in terms of conformations and energy, and remember, everything in conformations is about energy. What that means for us is that it is a much more energetically favorable conformation for the larger substituent groups to be equatorial than for them to be axial. And that, by the way, if we had multiple substituent groups, you would want the majority of your bigger ones equatorial rather than having them axial, and you're going to get a lot less strain that way. And again, that is the whole reason for doing any sort of conformations. If we were to do like, hey, these are both possible, right? So we're in chair conformation, that's the best conformation. But this particular chair conformation is going to be maybe 9 times as favorable as this one is. And so if we pulled a sample, most of it's going to be this way. It doesn't mean that none of it's going to be this way, but most of it is going to be this way because that's a much more energetically favorable situation for us. Okay? That's conformers. Remember that anytime we're talking about conformers, and we're going to talk more about different types of strain and all those sorts of things later on in the year, but this essentially wraps up conformers for us. Remember that you've got your 3 types of strain, and the whole point of doing any conformational shifts, any of those rotations either around the single bond or making the single bonds in the ring bend, is always to get to the lowest energy scenario. And so you're trying to avoid strain. You're trying to avoid torsional strain where the bonding molecular orbitals are overlapping. You're trying to avoid steric strain where they're actually physically constraining each other. You're trying to minimize angle strain, trying to get it back to the 109.5 degrees. Everything you do in conformers and conformations is what is the most energetically favorable state. All right? Thanks a lot, kiddos.